Hello again from Digicool Things. What you can see on my workbench is my testing setup for my TMS-9929A video display processor with an improved retro VRAM solution. But before we take a closer look at that, some background. Recently I missed out on an opportunity to buy an old Dick Smith Wizard computer/gaming console. Randomly discovering this auction listing brought back memories of working for Dick Smith in the 1980s, when we imported the Wizard as one of the earliest colour computers available to New Zealanders. The Wizard was of course just the local Australasian branding of VTech's CreatiVision system. This got me researching the CreatiVision to reminisce about the exciting games we were able to play in colour when these consoles first arrived in New Zealand, a country that had strict import restrictions in the early 1980s, meaning that most New Zealanders had not seen a colour gaming console capable of playing arcade-style Space Invaders and Pac-Man style games that you could actually play on your own television. It was an exciting time. I never owned a Wizard back then, as it was priced well beyond my lowly paid teenage pay packet, and all of my money had gone into a System 80 in those early personal computing years. Rediscovering the Wizard, or CreatiVision, reminded me that it was based on a 6502 CPU and the TMS-9929A video display processor. I'd spent plenty of time on 6502 assembly code later in the 80s, mostly on the Commodore 64, and I also had a TMS-9929A somewhere. I recall I'd wire-wrapped it up on a wire-wrap board to experiment with, just like the various other early video display processors I'd experimented with back in the day. Locating the Creative Emu pages and forum provided some good schematics and other technical information on the CreatiVision. I'll put the link to this in the description. So this was enough to trigger me into digging out my old TMS-9929A chip to once again have a play with it. I even found my original photocopied preliminary datasheets for this VDP in my boxes of old design notes and datasheets. And here's the old wire-wrap board I had. Which you can see has 8 4116 DRAM sockets, a couple of addressed code chips and the VDP chip, which I've since removed, and that was all wire wrap, not in the best condition anymore. And these were my old data sheets that I found in a manila folder, all photocopied back in the day from the supplier. Including preliminary data sheets, which are quite interesting, and even, what have we got here? I can't read the date on that, but the date's been chopped off. That's obviously a very early preliminary data sheet, and I think if you flick through you can see lots of hand-drawn notes, etc. Apparently prepared by Carlo Herman. It's an extension number and Labok. Don't know what that is. Anyway, quite interesting. These days, of course, I'll refer to the latest data sheets I can find. Note that the TMS-9929A provides PAL video timing. There is also a TMS-9928A and a TMS-9928A that provide NTSC timing. So firstly, some research to discover what others had done with this chip in more recent times. As many will know, the TMS-99 series originally utilised triple power supply 4116 dynamic RAM chips, and also typically used a colour encoder chip to produce a composite video signal, usually to an RF modulator output. Due to this, the video output actually seen on an old RF input television at the time was never fully up to what the TMS chip was actually capable of producing. Some hunting around determined that after several evolutionary projects, each one building on the findings of the others, the TMS-9929 or 28 optimal video quality output has recently been nicely resolved with the TMS-RGB add-on module. This 40-pin dip-size module sits nicely on a PCB's underside, attached underneath the TMS chip's 40-pin dip package, or preferably IC socket. This means the TMS-RGB module can pretty much be retrofitted to any TMS-9929 or TMS-9928 based system. So getting great video output from a TMS video display processor is a nicely solved problem. The TMS-RGB module was created by Nicholas Pygden. Hopefully I've pronounced that right. I'll put the link to his story in the description. So with the video solved, we can now look at an improved VRAM solution. Which VRAM chip should I use? Well, firstly, I'll point out that there is a later but less common TMS-9129 and 9128 or 9118 VDP variant, which instead uses two of the 4416 dynamic RAM chips. However, the TMS-9129 chips are much harder to obtain and significantly more expensive. So the next piece of research was to investigate an alternative to the 8 4116 dynamic RAM chips used for the 16 kbytes of TMS-9929A video RAM. Clearly, we should be able to avoid the need of a triple power supply, as just a single 5-volt power supply is desired. This led me to a PDF document dated January 2010, titled SRAM Replacement for TMS-99 VRAM by Tom Laments. This appears to be the VRAM replacement approach still being used by even the most recent TMS-99 VDP based projects that I could find. I'll put a link to Tom's story in the description below. Although the static RAM solution is over 10 years old and appears to be a proven approach, I wasn't overly happy with replacing 8 16-pin chips with a 5-chip solution that included a large 28-pin chip, 3 20-pin chips plus a 14-pin chip. You are therefore replacing an original 128 pin count memory chip solution, 8 16-pin chips, with a 102 chip pin count. Sure, you are achieving a single 5-volt supply solution, but in terms of the PCB real estate and PCB routing, you're only saving just 26 pins. So I thought I'd try a different approach. I didn't see the need to implement a static RAM solution, as retro dynamic RAM chips are relatively cheap and easy enough to get your hands on. In addition, the later DRAM chips are more reliable than the earlier 4116 devices. Also, sticking with DRAM would avoid the need to demultiplex the address output. The first seemingly obvious approach was to look at replacing the 8 4116 16K/1 chips with a couple of 4416 16K/4 chips, as used by the rarer TMS-9129 VDP. The newer 4416 chips are single 5-volt supply, so that certainly seemed like a logical thought. However, a quick check of the TMS-4416 datasheet shows that these use an 8-bit row address with a 6-bit column address. The TMS VDP and the 4116 DRAMs utilise 7-bit row and column addressing. So the 4416 DRAM chip with only a 6-bit column address is therefore not a viable option. This then led me to the 4464 DRAM chip. This is still an 18-pin single 5-volt DRAM, like the 4416, but it's organised as 64K/4. Now we don't actually need 64 kbytes, but the key is that the 4464 has an 8-bit row and column address multiplex, so we can happily use the 4464 with the 7-bit row and column address multiplex needed by the TMS VDP. We can simply hardwire the unused address line low or high. Note that hardwiring an address line does mean that half the rows and half the columns will not be accessed, and half the rows will therefore never be refreshed. However, that doesn't matter, as we only need the dynamic RAM rows that we're actually using to be read and refreshed. So now on to demultiplexing the data bus. The next issue to contend with is that the originally specified 4116 chips have separate data input and data output pins, allowing the TMS VDP to avoid a bidirectional bus connection. Instead, the VDP has only 8 data input pins for reading each byte, and a separate 8 output pins which output the 7-bit row and column addresses in addition to the 8 bits of data for writing each byte out to RAM. The 4464 4-bit wide DRAM chips have 4 bidirectional data pins, which in general use certainly makes sense, In addition, it's a requirement to allow it to fit into an 18-pin package. So, to interface 4464 chips to the TMS VDP will require gating the separate VDP input and output data connections to interface them to the combined bidirectional 4464 data pins. This isn't all that difficult, as we can simply connect the bidirectional 4464 data pins directly to the VDP's data input pins for reading. The issue is with connecting the VDP's 8 data output pins without causing any contention. Specifically, we don't want the VDP's output pins driving the bidirectional data connection at the same time as the 4464 is driving its data output. This can be solved with a single octal tri-state buffer to ensure the VDP's data outputs are only connected to the data bus when the 4464 is being written to. Okay, so then we need to satisfy the timing requirements. Having solved the potential data bus contention with a tri-state buffer on the VDP's data outputs, we need to be aware that this introduces a propagation delay, meaning that the data may not be available or stable when we are clocking the write signal of the 4464 DRAM. My initial thought was that instead of using a 20-pin octal tri-state buffer, I could instead use a couple of 16-pin hex buffers. For example, the 74LS367. The 74LS367 groups its hex buffers into a group of 4 buffers and a group of 2 buffers, each of the groups having its own enable pin. This would allow me to pair 2 groups of 4 from a couple of LS367s for the data bus, leaving 2 groups of 2 available to be used for delaying the write signal to the DRAM. However, this is where attention to the datasheet switching specifications is of significance. Firstly, if using the remaining buffers for introducing a matching propagation delay for the write signal, we would need to permanently enable these buffers. The write signal shouldn't be tri-state. In this configuration, we note that the datasheet shows that the input to output propagation delay, when moving from a disabled tri-state condition to an enabled state, can be more than twice the propagation delay of a pre-enabled buffer. As can be seen, TPLH, or propagation delay for a low to high transition, is a maximum of 16 nanoseconds, whereas TPZL, propagation delay for tri-state to low state, is maximum of 40 nanoseconds. Therefore, using a 2-buffer delay of the write signal will still not be sufficient to ensure that the write data is stable. 2 times 16 nanoseconds is less than 40 nanoseconds. We could add one, or both, of the other LS367 spare buffers to create a 3 or 4 buffer delay, but we will also need a way to deal with avoiding both the tri-state buffers and the 4464 DRAM data outputs creating their own driver contention, by them both driving the data bus at the same time. So with this in mind, and after a view of the different device datasheets, I came to the conclusion that a single octal tri-state buffer in a hex inverter would provide the best solution. After all, a 20-pin 74LS244 and a 14-pin 74LS04 added up to 34 pins, which are just 2 pins more than my original thought of using 2 16-pin LS367s. So let's take a look at optimizing propagation delays. A 74LS04 inverter has a typical propagation delay of around 10 nanoseconds, maximum of 15 nanoseconds. A 74LS244 octal buffer has a typical propagation delay from tri-state to low of 20 nanoseconds, maximum 30 nanoseconds, and a tri-state to high of 15 nanoseconds with a maximum of 23 nanoseconds. Based on these timings, a 2LS inverter delay of the write signal, which would be 20 nanoseconds typical, may be just adequate to ensure the data is stable at the right pulse edge. As we have 6 inverters to play with, we could provide options of a 2 inverter, a 4 inverter, or even a 6 inverter signal delay. But for comparison, the 74HCT04 inverter has a typical propagation delay of around 14 nanoseconds with a maximum of 25 nanoseconds. The 74HCT244 octal buffer has a typical propagation delay not that dissimilar to the LS244 of around 19 to 21 nanoseconds to transition from a tri-state to an active output. This actually looks to be providing a safer 28 nanoseconds typical using a 2-inverter delay. In addition, the 74HCT series are more commonly available and are often cheaper than the old school 74LS series, as well as being available in a nice hobbyist-friendly retro dual-inline through-hole package. So let's talk about avoiding bus contention. In order to significantly reduce the chance of data bus contention, the 4464 DRAM also has a handy output enable gate pin, pin 1, which when high forces the output buffers into a high impedance state, tri-state, something that the 4116 did not have or need. So to minimise the chance of bus contention, we can use the inverted right pulse to drive the 4464 output enable pin high during the period when the HCT244 buffers are driving the data bus. Conveniently, if we use the output of the first 74HCT04 inverter in the right signal propagation delay chain, we will disable the 4464 output buffers typically 14 nanoseconds after the VDP's right signal is asserted, but typically around 5 to 7 nanoseconds before the 74HCT244 outputs begin driving the bus. All sounds good. However, there is one other small timing constraint we should be aware of. That is, the required delay time from the 4464 output buffers being disabled, output enable pin is high, before data should be applied to the data I/O pins. The TMS-4464-15 datasheet specifies this as 30 nanoseconds minimum. While reviewing this timing diagram, it's also of relevance to note that the valid input data setup time before write is asserted is specified as a minimum 0 nanoseconds. That is, there is no additional data setup time required prior to asserting the 4464's write signal. Returning again to the minimum delay time from deasserting the 4464 output enable before data should be applied to the data I/O pins, clearly, with this specified as 30 nanoseconds minimum for the 4464-15, that's the 150 nanosecond part, then the 5 to 7 nanosecond delay between deasserting the 4464 output buffers and when the HCT244 outputs begin driving the bus appears to be inadequate. The solution to this is to simply move the HCT244 buffer output enable to be driven by the second stage of the hex inverter chain instead of being driven directly by the VDP's read-write signal. This is effectively adding 2 HCT04 inverter delays, or typically an extra 28 nanoseconds added to the original 5 to 7 nanoseconds extra HCT244 propagation delay. This satisfies this 30 nanoseconds minimum delay spec. Timing around the deassertion of the HCT244 buffer output enable also appears to be compliant with this additional delay. The 4464's delay until valid data output after the output enable is again asserted is specified as a maximum of 40 nanoseconds. Although the minimum is not specified, I am confident that we'll avoid any driver contention. So to summarise, my proposed updated retro VRAM solution for the TMS-9929A or 28A VDP would involve two 18-pin 4464 DRAM chips, a single 20-pin 74HCT244 octal buffer, and a single 14-pin 74HCT hex inverter. Original 74LS series may also be used, but based on the satisfactory timing of the HCT devices, the general availability, the typically lower price, and the lower load and power of the HCT CMOS devices, HCT would seem the preferred approach. This brings us to a total pin count memory chip solution of just 70 pins. This, quite satisfyingly, delivers on my desire for an improvement over the 2010 static RAM solution's 102 pins, by a significant 32 less pins. This is great in terms of required PCB real estate and also the added ease of PCB routing, or perhaps even just a welcome 32 less connections required if wiring this up on a breadboard. So my next step was to then capture my circuit idea into a KiCad schematic, which I'll link to below in the description. With a schematic done, it was time to pull out a breadboard and test the timings in practice and confirm the new design. In order to thoroughly test the design, I connected up a TMS RGB module for high quality video output and used an Arduino to drive the TMS-9929A. That's what you can see on my workbench. An Arduino sketch was then written to test both the TMS-9929A and to perform multiple pass, varying bit pattern read-write tests on the full 16K byte VRAM. Interestingly, I had previously made an Arduino-based DRAM chip tester, but it occurred to me that testing the DRAM via the TMS-9929A actually provided a real-world access timing-based DRAM test, as compared to the practice of toggling the pins of a DRAM chip directly via an Arduino's GPIO to simulate DRAM access and timing. So I'm pleased to advise that my circuit passed all the tests without any issues, including tests around multiple DRAM chips with various common speeds of 100 nanoseconds, 120 nanoseconds and 150 nanoseconds, i.e. the -10, -12 and -15 suffixes. I in fact used the circuit to test my entire stock of 4464 DRAM chips. So let's take a look at the Arduino sketch, and then we'll also have a quick look at the TMS-9929 output on my video monitor. Okay, so this is my Arduino sketch for testing the TMS VDP with my alternative VRAM solution. So I'll just quickly step you through this. You can see the output at the moment on the console monitor. It's just scrolling through testing the backdrop colours of the VDP chip. Okay, so starting from the top of the sketch, you can see I have a description of the pins that are used, how to connect up the TMS to the Arduino. There are 4 control pins, the mode pin, the chip select write, the chip select read, and the reset pin. And apart from that, we've just got the 8 data bus pins. So I've just got a couple of notes here just saying the VDP IC is tested via stepping through the 14 different backdrop colours. That's the backdrop and the border. VRAM is utilised for displaying a single 8x8 graphics 1 pattern in all 768 screen positions. There's a test VRAM routine which does a multi-pass test of the VRAM using either a nibble or a byte pattern. The reason I've got that option there is the circuit you saw on my desktop has only one 4464 DRAM wired up, because it wasn't necessary to add both the DRAMs just for testing this proof of concept, as only one DRAM chip is actually required to test this circuit. I've got a note there to open your serial monitor so you can see the progress and the VRAM test result reporting. Okay, so first we define the TMS VDP's control pins, which, as I mentioned before, there's 4 pins involved, so they're just defined there. Then I go down to defining the 2 options for the mode pin, which is either VRAM access, where the pin is low, or register access, where the pin is high. Then we have 2 core VDP read and write access functions. So read byte VDP passes a parameter of whether you're accessing VRAM or register, and that will return a byte. And write byte VDP, you pass the byte you want to write, and also the mode selection of whether you want to write to VRAM or to a register. Then we have some additional fundamental VPS access functions. we have set VRAM read address, where you set up the address where you want to start reading bytes from the VRAM. Similarly, there's a set VRAM write address, which is again for setting up the address that you want to start writing bytes to VRAM. There is write register byte VDP, which actually performs the write of a byte to a specified register. Okay, the next set of routines we have convenience functions. So these are basically just wrappers for the core read and write VDP functions, just to aid readability of your code. So first we have read status byte VDP, which simply, as you guess, reads the status byte from the VDP. And we have a read VRAM byte VDP, which reads VRAM byte, and of course a write VRAM byte VDP, which similarly writes a VRAM byte. We then get into some general utility functions in the sketch. These first ones here, num hex digits, hex string, and bit string, are just simply for returning a string of either hexadecimal digits or binary digits for displaying the data in the console output. Right, then we have our VRAM test function. That returns an integer value, basically a 1 if the test is passed okay, or a 0 if a failure is detected. Now, firstly, there's an array of test values, and I've got writing a 0 byte, an FF byte, a 55 byte, and an AA byte. And you can see I've actually got an alternate set of test values which just include the lower nibble. And that's because, as I say, I'm testing the circuit just by wiring up a single 4464 DRAM in the lower nibble of the byte. Okay, and then we just go into a loop where we test each one of those patterns, and then within there's another loop where we write the test byte into all 16K locations of the VRAM, and then we go and read them all back, all 16K locations of the VRAM. And for each one we compare the byte to the byte we expect. If there's an error, it doesn't match, we set a test fail flag and we break out of the loops. If there's a test failure, we report the address of the failure, the byte we wrote, and the byte we read back. Otherwise, if we successfully test all patterns across all 16K of VRAM, we report all tests passed. Okay, the next routine is VRAM clear, where we just simply write 00 to all 16K locations of the VRAM. We have a VRAM setup. Now this is where we set up the pattern, name and the color tables, specifically for the graphics 1 mode where we're running the tests. First off, we're setting up just a single pattern as pattern number 0 in the pattern table. I've commented out a loop because, if you want to write the same pattern throughout the entire pattern table, you can. I've also commented out a second one where I had a byte-wide test pattern, but the first one is just simply writing a pattern that uses only the lower nibble, because as I say, we're just testing a single 4464. So if we assume the top nibble isn't there, we can just test for a image in the lower nibble. Okay, and then currently I have commented out a simple VRAM test, which was my initial test where I just simply read back the 8 bytes of test pattern 0 and output them to the console so that you could actually see a very quick test that the pattern that was written has actually been read back successfully. Okay, then we set all 768 screen locations in the graphics 1 mode to be pattern 0, to display pattern 0. Then we set up the color table, and here we only need to set up the first byte of the color table, because each byte of the color table in graphics 1 mode determines the color of 8 patterns. So the first byte will determine the color of the first 8 patterns, patterns 0 to 7. Again, I've commented out a loop where I could write a color byte to all 32 colour table locations, which would specify the same colour for all 256 possible patterns. As you'll note, I've fully commented my code so I can remember what everything does. For the colour table, you can see in my comments the upper nibble defines the colour of on bits, and the lower nibble defines the colour of off bits. And of course, since we're only using a single 4464 in the lower nibble, effectively the upper nibble is always going to be 0. And 0 is the transparent colour. So for our single 4464 test, the colour table is effectively saying any bits that are on in our pattern will simply be transparent. In other words, you can see through to what the background or backdrop colour is. Whereas we're setting 1 in the lower nibble for the off bits, and 1 corresponds to black. So all the on bits in the pattern will be black, and all the off bits will be transparent, showing the backdrop colour, which is adequate for our testing. Okay, then we have the towards the end of the program here, we have the Arduino standard setup function, where we set up the serial port. Then we set up the Arduino's control pins as outputs and in a not asserted state. Then we reset the VDP by pulsing the reset pin low. Next, we initialize the VDP registers, and I've fully commented here on what all the bits of each register do. There's a total of 8 registers. First register, you can see we've set up graphics 1 mode. Second register has various control bits in it, including also the graphics mode. So we've set that up for graphics 1 mode with 8x8 pixel sprites, selecting 16 kbytes of VRAM, and also the display area is enabled. So that display area enabled bit enables you to actually disable the active display area. The border is still shown, just the active display area is either disabled or enabled. Register 2, we've set that is the name table start address. So we've set that up to start at address 1400. Likewise, register 3 is the colour table start address. We've set that to start at 2000. Pattern table start address is set up to start at 0800. And the sprite attribute table, which we're not actually using in this test, we've just set up to start at 1000. And the sprite pattern table, which again we're also not using in this test, is set up for the 000 address. That leaves register 7. The lower nibble controls the colour of text mode off bits and also the border and backdrop colour. So that's what we'll be using to test the VDP by transitioning through the various backdrop colours. That's independent of any VRAM, so you can actually run that test without having any VRAM installed or connected. The upper nibble of register 7 sets the text mode on bit colour. Right, in this once-off setup function, we then call the VRAM test. We then call VRAM clear to clear the memory, and then we run the VRAM setup, and we're done. Now I've made a note there that we do that if we just want to run the VRAM test once. The other option is to comment this out and within the loop actually run the tests repeatedly, which I've also allowed for. Okay, so looking at the loop, we set up for the loop, we've set up an array of colour descriptions just for making a tidier console output, and we have a count for how many VRAM tests were successful and how many have failed. So here you can see I've currently got commented out the option of repeatedly running all the VRAM tests in a loop and maintaining a count of how many successes and fails we've had. And lastly, we just simply have the standard loop of rotating through the backdrop colours with a 2-second delay. And there are of course 16 colours 0 through F available to the VDP. But colour 0 is basically transparent and colour 1 is black, so hence I'm just rotating through the 14 different backdrop colours, colour 2 through 15. Right, and you can see that running. I'll just upload that now so you can see the console reset and the initial test of the VRAM run. So that's compiling. Uploading, and there we go, testing 16 KB VRAM. You can see the test patterns in the lower nibble, all the tests passed. Then it does the setup, and you can see it's now just toggling through the backdrop colours every 2 seconds. What I might do is I'll just comment out the looped memory test, and I'll comment out the once off test run, and I'll run that, and you'll be able to see the repeated VRAM tests running. Okay, now you can see on the console that we've got a repeated loop that is changing the backdrop colour, but also in every loop we're going through and testing all 16K of the VRAM locations with the multiple bit patterns. And I'm keeping account of the success and fail. Now I have run this for a considerably long time, and I've had absolutely no fails whatsoever on the VRAM tests. Yeah, and you'll just notice here I've also included disabling the display area during the VRAM test and re-enabling it after the VRAM test, just to avoid showing the striped pattern that occurs when we're testing the VRAM. And you can see we're now up to, what are we up to? 24 successful tests with no fails. Right, so what's my next step? With my improved retro VRAM solution circuit tested and confirmed, I'll next create a TMS-9929A or 9928A VDP board for my new Minimalist Europe Card Bus design, MECB. This will then allow me to easily experiment with my TMS-9929A with whatever 8-bit CPU or memory map that I choose. But until then, that's it. Thanks for watching.